So far, we have one definition for a product of vectors, right? We've talked about the dot product extensively. We've derived some nice properties of the dot product, or a couple of nice things. So what I'm going to do is we're going to define a new product. With the dot product, we sort of had some kind of intuitive motivation. We ended up landing there by starting with the product, if we recall. The dot product, we said this. We said, hey, the definition is going to be A dot B equals the norm of A times the norm of B times the cosine of the angle between them. Okay. And then from there, we're able to show through a nice couple of pages of algebra and so forth that A dot B could also be found by doing the product of the components added together. Okay. So we were able to do that. Today I'm going to start differently. I'm going to tell you what the cross product is, and then after telling you what the cross product is, derive some pretty properties of the cross product, and then maybe prove a couple of properties it has, and we'll go that direction. Okay, so the cross product. Ready? We write this A cross B, and it's equal to the following. And I'm going to write it this way. You're going to be surprised. Okay, here we go. So the first thing is going to be A2B3 minus A3B2. And I want you to notice right away that this thing we're writing is not a scalar quantity, is it? See, the dot product yielded a number, a real number. It was a product of vectors that gave us back a scalar. This is not happening. In this case, we're actually getting a vector back. A3B1 minus A1B3. And then the last component is A1B2 minus A2B1. Okay. I guess we're going to be formal about things. I'll say where A equals the vector whose components are A1, A2, A3, and B equals the vector whose components are B1, B2, B3. Okay. So now that we have that, you might think to yourself, I don't know if I'm going to be able to remember this or whatever. And if you watched the other video, or you remember last time I talked about determinants, you might say, what do determinants have to do with this? Okay, well, let's start. Ready? I'm going to do this. We're going to write a special matrix down. I'm going to write this matrix, and its first row is going to be the vectors I, J, and K. Just to remind you, I is the vector 1, 0, 0. J is the vector 0, 1, 0. And K is the vector 0, 0, 1. And what I'm going to do is I'm going to put the components of vector A in the second row of this matrix. And I'm going to put the components of vector B in the third row of this matrix. Okay? Now you'll notice I didn't give this matrix a name yet. We're going to leave that off. I'm just going to put a little question mark next to this for the time being. We'll name it in a little while. All right? What we are going to do is we're going to remember how we did the determinant and apply that here. So the determinant, denoted DET, of question mark equals. And if you remember, we talked about expansion by minors last time. Right? So we're going to expand by this first row. Okay? And if we do that, we get the vector I times its minor. Minor of vector I, we crossed out the first row in the first column, would be this matrix. So that's going to be A2, A3, B2, B3. Some of you might see this already, but if not, you're going to see something very pretty in a moment. Okay. We remembered that we have to do plus minus plus. We had that checkerboard of positive and negative signs. So it's going to be negative J times its minor. The minor of J would be A1, A3, B1, B3. If you're in doubt about that, imagine covering up the column that had J in it and the row that has J in it, and this little matrix right here is what's left over. Lastly, plus K times its minor, and that minor would be A1, A2, B1, B2. Alrighty. So, let's do a little bit more work with this. So when you look at this first part of this sum, you should notice that this thing I is a vector, and this determinant here is actually a scalar. Determinants yield the number. So you have a scalar times a vector. So let's write this out. You're going to have the vector 1, 0, 0 times the scalar A2, B3 minus A3, B2. Because that's what it means to do the determinant of a 2 by 2. You multiply those guys and you subtract the product of those. All right. Minus J times, now J is the vector 0, 1, 0, times the scalar coming from that 2 by 2 determinant, which would be A1, B3 minus B1, A3. And then lastly, it's going to be plus the vector K, which is 0, 0, 1, times the scalar from that determinant, which is going to be A1, B2 minus A2, B1. All righty. So there's something nice about this sum of vectors that you're having. What's nice about it is, if you look at the first expression, if you take this vector times this scalar, in effect, the only thing that happens is this scalar here ends up going into the first position of the vector. And then when it gets multiplied by 0 for the other two positions, those will come back as 0. So this first vector that we get looks like this. A2, B3 minus A3, B2, 2, comma 0, comma 0. Oh, that's nice. All right, now I can't quite fit this, so let's use we'll go to this one. Now we'll look at this one here. What's that going to give us? It's going to give us the vector, it's going to be 0. Now let's be really careful. There's a negative here, so that's really a negative 1. And when I take that negative 1 and I multiply it by this thing over here, what do I get? It becomes B1A3. This second term really becomes positive, and I'm just going to write it in the first position. And then this thing here becomes minus A1B3. And then we have comma 0. Okay. And then lastly, we will take this vector times this scalar, and that's going to give us, all right, a vector 0, 0. And then 1 times this scalar is just that scalar. Okay. So at this point, you might feel like a little beat up by a bunch of algebra, right? A little black and blue. Black and blue. Never mind. Bad joke. Okay. So we're going to add these together, but it's really easy to add these, isn't it? Because this component gets added to 0 and 0. And then this component here gets added to 0 and 0 up here. And then this component down here gets added to 0 and 0. So we just end up with the sum of these things is going to be A2, B3 minus A3, B2, comma, B1, A3 minus A1, B3, comma, A1, B2 minus A2, B1. And if you take a careful look at this resulting vector, I just introduced you to that maybe 5 or 7 minutes ago, right? A good name for this would be A cross B. So what does this mean? It means that the cross product of two vectors can be thought of as the determinant of a very special matrix. So we can think of this as the determinant I, J, K, A1, A2, A3, B1, B2, B3. Okay. So let's do an example. Let's just start with two vectors and find the cross product, and then we're going to look at the result and see what we can say about it. All right? So actually, well, let's consider this. Let's let vector A equal the vector 1, 3, 4. And vector B is going to be the vector 2, 7, negative 5. Okay? Okay. So you should try this on your own. I'm just going to proceed with this calculation here. I won't talk while I do this. So this should have been your first step. Let's finish. So this is going to equal. Now, I'm going to write this one more time with these components and these vectors in front, these unit vectors. But at some point, you may stop writing that. And you might just say, hey, wait a minute. That determinant always ends up in the x component of the vector. And you might realize that this determinant, the negative of it, always ends up in the y component. And you might notice that this determinant always ends up in the z component. So you might notice that after a while. I'll write it one more time with these unit vectors in front. So here we are. We're going to get 3 times negative 5, which would be negative 15, minus 7 times 4 is 28. And then you're going to have minus j, which is this vector, times the component is going to be negative 5 minus 8. And then plus k, which is 0, 0, 1. Make that neater, times 7 minus 6. So when everything's said and done here, you should get, looks like negative 15 minus negative 28, so it's going to be negative 43 in the first position, comma, negative 13 in the second position, and then positive 1 in the third position. You could also write that if you wanted to, negative 43. Oops, one mistake here I forgot. See, and this is easy to do. Don't forget that negative. So this is actually a positive 13 plus 13j plus k. So it's sort of fun to write it this way, because then it kind of reminds you of how you created this thing, right? It was vectors times scalars, right? And that's what this expression is down here. You got the scalar negative 43 times the vector I. You got the scalar 13 times the vector j. Okay, fine. So we did this. All right. So now I'm going to ask you a question that should lead us to some kind of discovery. I'd like to know something about this vector. Turns out this vector has a couple of cool properties. But I'd like to know something about it related to the vectors I started with, right? Dot products sort of had nice things, right? We knew if we took the dot product of two vectors and we got 0, that the vectors were perpendicular, right? Now, we're taking the cross product of two vectors and getting another vector. And the question I'm asking is, how is that vector related to the two vectors we took the product of? Right? So let's actually do something. And since I just mentioned about dot products and perpendicularity, we know how to test for perpendicularity pretty quickly. So let's recall the vector A was the vector 1, 3, 4. We had the vector B, which was 2, 7, negative 5. And we have A cross B equaling negative 43, comma 13, comma 1. All right. So what I'm going to do is, I'm going to do this expression, A dot A cross B. Saying, let's take one of the vectors that I had cross product, and let's dot it with the A cross B. Let's see what happens. All right, so if we do that, dot products, we remember, just mean take the x components, multiply them, add them to the product of the y components, then add them to the product of the z components. Okay, so if we do that, we're going to have 1 times negative 43. Actually, I'm writing vector notation. I shouldn't do that. This is going to be a scalar. So you have negative 43 times 1 plus 3 times 13, okay, plus 4 times 1. Let's see what happens here. So we get negative 43 plus 39 plus 4. But that's 0. So what do we know now? That tells us that A must be perpendicular to the cross product of A and B. That's sort of interesting. So now we have a sense of maybe where A cross B, how it looks in relation to vector A. Let's also check the cross product between B and A cross, the dot product between B and A cross B. See what happens there. Okay, so we're going to have 2 times negative 43, and when I multiply the x components, plus 7 times 13, plus negative 5 times 1. All right, so what do we have here? We have negative 86 plus 91, right? Yep. And then minus 5. Oh, wouldn't you know it? Well, that's 0 also. So now we also know that B is perpendicular to A cross B. Okay. So there you go. So we've shown that, at least for this example, right? We had 2 vectors. We found the cross product. The vector that we got back from the cross product was perpendicular to 2 vectors that we had crossed to begin with. All right. So the fair question is, would that always happen? And to answer that, you just need to do a quick proof here. Okay. I'll do it with one vector, and then you can do it with the other. So you have 2 vectors, A1, A2, A3, B1, B2, B3. This is vector A. That's vector B. A cross B, by definition, was A2B3 minus A3B2, comma, A3B1 minus A1B3, comma. All right, so now, lastly, we're going to have A1B2 minus A2B1. Okay. So all we're going to do is we're just going to do A dot B, A cross B, and see what happens. All right, so here we go. That's going to be A1 times this first thing. So I'm going to distribute that A right into there, might as well. So I have A1, A2, B3 minus A1, A3, B2. And the dot product says, okay, after you multiply the x components, add that to the product of the y components. So I'm going to say plus, and if I take the y components, it's going to be that times that. So I get A2, A3, B1 minus A1, A2, B3. So I guess maybe we can do this to make it clear. Okay, so this little piece here was the product of the x's. This second piece over here, this thing I just put parentheses around, this is going to be the product of the y's. And then lastly, we're going to have the product of the z's. So that's going to be A3 times everything in here. So we would get A1, B2, A3 plus minus A2, B1, A3. So this is coming from the z's. Okay. Now we're expecting this, or we're hoping. Oh, don't forget my minus here. We're expecting this to be 0. So let's see what happens. Let's look for copies of terms. Here is A1 times A2 times B3. Where is that? A1 times A2 times B3 is right here. So this is plus and this is minus. They're gone. Okay. Looking good so far. This one has A1, A3, and B2. So A1, A3, B2 is down here. Those guys cancel. And then hopefully those other two match. What they do, A2, A3, B1. Here is A2, A3, B1. They cancel. So sure enough, you get 0. Okay. You could do the same thing for B dot A cross C. And what I'm showing is that the cross product, the vector you yield, is always perpendicular to the two vectors you crossed at the beginning. Okay?